Hey everybody, welcome to today's video. This is about writing a net ionic equation for reactions that happen in aqueous solution. So I have an example here. These are the reactants for a single replacement reaction. And in first year chem, you learned how to use an activity series to predict the products. So when we write a net ionic equation, we're going to start with that same step. If the products aren't given, you're going to use your activity series to predict them and then balance the equation. So I have a single metal here, and it's going to try to replace the metal in this compound, copper. And when I look at an activity series, what you learned in first year chem was that the metal higher on the activity series is more able to replace or kick out any metals below it. Here's magnesium, and sure enough, copper is far below it. So I can predict that magnesium will kick out the copper. Now the copper is going to stand alone as an element, and because copper is a metal, I know that exists as a solid when it's by itself. And the other product is going to be between the magnesium and the bromine. Now, before I write that formula, remember I refer to my periodic table to see that magnesium has a 2+ charge as a cation, and bromine has a 1- charge as a halogen. So my product is going to be magnesium, which is 2+, and bromide, which is 1-, and that results in this compound. All right, you learned how to do that in first year chem. The next step would be, of course, to balance this equation, and this one is easy because it's already balanced. Now, if we're going to turn this equation, which is referred to as a molecular equation, and it's perfectly valid, but because so many reactions in chemistry do occur in aqueous solution, we like to write it in terms of a net ionic equation, and the purpose of that is to focus in on the species that are actually doing something new. And we're removing or ignoring any species that are just hanging out watching the show. Okay, I'll show you what I mean by that. So my next task in writing a net ionic equation is to look for any species that I know dissociate into ions. And I'm going to separate these into cation and anion and then write the charge for each. All right, so I have here an ionic compound that is labeled AQ, and that's my hint. I know that means that in this aqueous environment, this is not going to exist as formula units, but instead it's going to be separated into copper cations and bromide anions. Now, I want to pause for just a minute and show you what's happening in the beaker. When this ionic compound went into solution, remember in the dissolving process, the action of the water molecules physically rips the cations and anions away from each other. Notice that I ended up with one copper cation and two separate bromides. So when it was in its solid state or before it went into solution, the copper and the two bromides were all ionically bonded to each other. But now that they're in solution, I have one copper and two separate bromides. Okay. These bromides are not hooked to each other. If they were, you would write Br2 with a 2 subscript. But in solution, they are two separated individual anions. All right, now notice that I'm also going to be on the lookout for ionic compounds that are not labeled AQ, but I have some previous knowledge that this does dissolve. You'll be learning more about that as we move through the unit, but for now I'm just going to tell you that I have knowledge magnesium bromide does dissolve in water. So I am going to separate this one into cation, magnesium, referring to the periodic table, magnesium in column 2A would have a 2+ charge as an ion, and I'm going to have these two individual bromide anions, each of which has a -1 charge. Okay, now the next step in writing a net ionic equation is to look for any molecular species which need to remain intact. All right, I don't have any of these diatomic elements which exist as molecules. I don't have any of these common molecular compounds, and nor do I have any weak acids. But I also want to be on the lookout for anything that common sense just tells me is a solid that doesn't dissolve. Metals, for example. So magnesium is a metal, and when you put it in water, it stays as a solid metal made of atoms. So I'm just going to rewrite that one as is. And on my product side, the same thing is true of copper. Copper metal in a beaker of water is just going to exist as a chunk of solid copper. All right, so what I've got here is aqueous materials that I know dissolve. I've shown them as separated ions. And the things that don't dissolve, I've shown them as solids. Okay, the last thing to do is to look for any species in this ionic equation that are exactly the same on the reactant side and the product side. Okay, be careful here. I have magnesium on both sides, but notice there has been a change. As a reactant, magnesium consisted of solid atoms, but through the course of the reaction, it got more positive. It turned into a positive cation. We call that process oxidation, and we say that these magnesium atoms were oxidized. The best way to remember that is that oxidized means you get more positive. Sorry for exaggerating those vowels. Oxidized means you get more positive. And the way that happens is by losing electrons. So the magnesium atoms, which are high on the activity series. Now, do you see how this arrow is labeled ease of oxidation? Magnesium is very easily oxidized. It loves to give away its electrons, and it gives away electrons. In so doing, it becomes a cation. So there has been a change in this species. Now, when magnesium gave away its electrons, that's called an oxidation half reaction. When it gave away its electrons, those electrons don't just get to go into the beaker of water. Instead, they have to land on somebody. And these electrons are going to be attracted to this cation. Opposites attract. So these electrons will be snatched up by the copper cations. And when copper cations grab 2 electrons, they turn into neutral copper atoms. So this species has also undergone a change. But notice that my 2 bromide anions as reactants are still exactly the same as products. In other words, they sat in that beaker and watched the magnesium and the copper do something, but the bromides themselves did nothing. So we call them spectator ions. And if I remove those from this full ionic equation, the pieces left over, the magnesium solid atoms and the copper cations swimming in solution, turned into copper solid atoms, neutral, and magnesium cations swimming in solution. This, with the spectator ions removed, is known as the net ionic equation. Okay, let's take a look at what was happening in the beaker. We started out with one reactant, copper bromide, in solution. So I know that when this solid material went into the water, the action of the water molecules separated the cations and the anions. And then I added the chunk of magnesium metal, and because that magnesium is very easily oxidized, the magnesium atoms gave away 2 electrons which were attracted to the cation. The cation then became neutral copper atoms, sank to the bottom of the beaker, and the magnesiums and the bromides, important part there, when the magnesium gave away its electrons, it became a cation. And now we've got cations and anions free to swim around in solution, which, by the way, means that's an electrolyte. Okay, let's do one more together. So our first step is to predict the products and balance the equation. Sodium, the metal, is going to try to kick out or displace the metal iron. I refer to an activity series, and sure enough, I see that sodium, which is above iron, is more easily oxidized. So sodium is going to kick out the iron. Now the iron is going to be by itself as iron atoms, solid, and the sodium, which got oxidized, got more positive, turned into a cation, is going to make a compound with nitrate. Okay, so I know sodium becomes a 1+ cation, and I remember from first year chem that nitrate, the polyatomic ion, has a -1 charge. So my new compound that is formed out of a +1 cation and a -1 anion is sodium nitrate. All right, now I'm going to balance my equation. 1 sodium went in, 1 came out. 1 iron went in, 1 came out. 3 nitrates went in. To show that 3 nitrates came out, I'm going to put a 3 here, which also shows 3 sodiums coming out, so I'm going to put a 3 there. Okay, first 2 steps are done. This is known as the molecular equation. Net ionic equation has you considering next any species that dissociate into ions. Primarily, I'm looking for anything that's labeled aqueous, as this one is. So I know that in solution, this iron 3 nitrate actually exists as iron 3+ cations swimming in solution, and 3 separate nitrate anions swimming in solution. All right, I'm also going to be on the lookout for any ionic compounds that are not specifically labeled AQ, but I have prior knowledge that they do dissolve. As you'll learn as we go along, any compound that has sodium in it is going to be soluble in water. So I know this compound dissolves in solution. And I'm going to have 3 separate sodium cations in solution, and I'm going to have 3 separate nitrate anions also swimming in solution. The next step is to look for any molecular species that remain intact. I don't have anything here, but I do know that solid metals elements exist as neutral molecules in solution. So these 3 sodium atoms are solid, and I'm going to write them that way. And the iron atoms in solution are neutral atoms sitting at the bottom of the beaker. What I've just generated here, it looks kind of messy, but that's the complete ionic equation. The last piece of business is to look over carefully and find any species which are exactly the same on the reactant and product side. 3 sodium solid and 3 sodium ions aqueous, not the same. This is actually the oxidation process that's going on. These sodium atoms, which are very easily oxidized, are going to oxidize or get more positive by losing their electrons. Each of these gives away 1 valence electron for a total of 3 electrons given away and 3 sodium cations produced. The iron cation is going to grab up those electrons that were just given away, and 3 electrons landing on this cation is going to turn it into a neutral atom. Notice, however, that my 3 nitrates are not doing anything new here, and they are written exactly the same way on the reactant side and the product side, which means they are spectator ions. And as we write the net ionic equation, we simply remove those. They're in there. It's just that they're not doing anything. They're not changing in any way in the course of this single replacement reaction. So we just take them out of the picture. It just kind of cleans things up. And this is the net ionic equation for the single replacement reaction that happened in solution. Okay, guys, I hope that was helpful.